Hey everyone, and welcome back to our first class post-VW date. Ooh. Congratulations in advance for finishing the course, because at this point you're going to finish the course, whether you like your final grade or not. So, today we're going to talk about profiling a bit. So, following along with the example is optional. I keep saying this course isn't about C, but we're using C as examples for more generalizable concepts. This is a huge example of it. These C profilers are not things that I've used before, not things that I've even thought about after I finished this class, but I have used profilers in general, and you very much should know what a profiler is. Yeah, I don't think I've mentioned profiling before. This might just be gibberish at this point. So I'm going to leave this slide up for a couple, maybe a minute or so, a couple minutes. And also, assignment 3 sure is a thing. If anyone has any questions while I'm keeping this slide up, ask away. In about 10 seconds, I'm going to move on to another slide with yet more things that you might want to download. These slides are available on UMLearn as well, by the way, so if you miss something, it's not lost forever. Okay, I think we're going to get started soon. And are you all sure you don't have any questions about assignment 3? It's very difficult, and a lack of questions is much more likely to mean that you haven't started yet than that it's easy and you're doing fine. So, I don't know, be intimidated, take it seriously, ask any questions you need on the discussion forums, I guess. So, what are we going to do today? We're going to talk about optimization and more emphasis this lecture on how to figure out when you need to make optimizations. So, like I mentioned last class, taking a sort of more high-level view of optimization is often more helpful than changing things at a super low level. We are going to look at some low-level optimizations very soon in the course. C lets you actually take a struct and then choose exactly how its bits will be laid out. But we're going to talk about that, explain how it might be useful in some cases if you're working on really constrained hardware, which still happens in the modern day with embedded systems. But we're going to talk about how most of the time, usually, things like using better data structures will speed up your code more meaningfully. So, what the heck is profiling? This should probably remind you a bunch of the debugging lecture, except your code works, and you get how it works. But it's slow. No one likes slow code. Or maybe you've written code that you think is nice and efficient, but you've given it to someone else who's found a way to make your code absolutely crawl. Maybe you have algorithms that work well in a general case, but slow down significantly on an edge case. Quicksort might be a good example of this. Or maybe you've been given code written by someone else who hopefully understands how it works, but it's very slow. So, what do? Pretty similar techniques to debugging. The moral of the story that we'll eventually get to is that you should totally use dedicated tools, but these simpler techniques that I'm about to talk about can still be useful for simpler cases. Spelunking. You can use printf, basically look around the code for things that are doing more work than they should, or maybe put printfs in important functions and see what's being printed the most. Hopefully that corresponds to functions being called often, which hopefully corresponds to things taking a long time. Maybe. So more on spelunking. It's just reading the code and mentally executing it. So you might be able to find spots in your code that are doing more work than necessary. I'm trying to think of a good example other than the one that's about to be in the slides. Maybe you're just iterating through a list more often than you have to. Actually, one thing that someone identified on the test that wasn't the intended answer was that one question with the copy string function that was dangerous because it didn't do any bounds checking and didn't copy the null terminator. It had a call to strlen in its for loop header, which meant that it was calling strlen every time it iterated, and that was a waste of time. So that's a simple enough optimization case that you can identify by spelunking. So using printf, you could see where the printing slows down or stops. You'd basically watch the program's execution and see when, or just watch when it slows down. This can help you understand the flow of the application, like what functions are being called and when. And yeah, just identify what the flow is like when the code slows down. And if it isn't observably slow, I guess you're screwed. Printf really isn't the best tool for this. And also keep in mind that in many cases, printing itself can be slow. I think I mentioned in a previous class a game that had repeated print statements for debugging purposes, and we couldn't figure out why it was going so slow, but it turns out all those print statements were slowing it down. This was in C#, by the way, which is basically Microsoft's version of Java. So this is not a C-specific problem. So, do you just whack your computer like last time? Of course not. You can finally figure out what a profiler is. It's a tool to help identify how long code takes to run. And there are many of them. Oftentimes, IDEs will have a profiler built in, and there are other ones that you could run separately from your text editor. We're going to look at two. One of them is gprof. I think that stands for GNU Profiler. GNU as in GNU/Linux. And Valgrind and Kcachegrind. The name Valgrind might sound familiar because it's mentioned in the assignment 3 description. You're eventually going to use Valgrind not to analyze performance, but to analyze memory usage. It's impossible to truly detect memory leaks. Pretty sure that would require having a solution to the halting problem, which you'll hopefully learn about if you're cool and you take Comp 3030. But a tool like Valgrind can help show you places where there are likely to be memory leaks and also identify easier, obvious, from its perspective, cases of memory leaks. So to use gprof, there are 3 steps. First, you compile your code with the -pg flag. You may remember -g gives you debugging symbols. This does, I think it does that too, and more. And then you run your code without actually doing anything different, really. But having compiled your code with the PG flag, it essentially inserts code to run gprof into your code. So running the code normally will generate a report that you can then open with gprof. Here's another terminal tip. If you've got a bunch of boring output and you want your terminal to be nice and pristine, clear. It's easy as that. So I've got an example of a piece of code that you might want to profile on my Aviary account. It's not a very interesting piece of code. Definitely don't need to type along. You barely need to read along. You just need to know that there's a pair of functions in it that take a really long time. And this is the long-running function in question. It just stalls for time. Array I plus equals array j doesn't mean anything. You can and should suspend your disbelief and pretend this is doing some useful work, but the point of this code is that it runs one loop in a loop inside of another loop, each of which runs for this many iterations, which is that many. I don't know how much complexity theory you know, but this should look pretty bad. Although, at least, depending on who you ask. In practical terms, this is very bad. If you're talking to a complexity theorist, they'll say, at least it's polynomial time. And if you talk to a computability theorist, they'll say, at least it's computable. But we're actually going to run the code, not just write it down and stare at it and do math on it, so it's bad. Heavy computation 2 is literally the same thing as heavy computation. And there's a main line that runs both of them. I'm going to compile it with the PG flag and run it. still surprisingly fast. You might have seen there's a little delay before the next prompt showed up. It actually takes a lot to make that delay. So this code was running for a really long time by C standards. So now we have a file called gmon.out. Its contents aren't very useful. In fact, they're completely unreadable by human eyes. But we can read them by entering gprof heavy, or gprof, the name of your program. And as spoiled by my command history, or the autocomplete, I was looking at this before and found that gprof just prints to standard output, which is pretty annoying and hard to work with. So I'm going to pipe it into less. And then we see a profile of it. We see that both heavy computation and heavy computation 2 took up roughly half of the runtime each. It's kind of interesting that heavy computation 2 took more time despite doing the exact same thing. I believe that may be because the memory in that big array is the same for both of them. So heavy computation 2 is starting with larger numbers. And addition is basically constant time in practical terms, but it's technically linear time of the number of bits in the variable. So I bet there's some optimization going on that skips a bunch of additions of 0 for small numbers, like because they would have several 0 digits. But I'm not much of a systems person, at least not anymore. This could also just be random coincidence variation and stuff. This example was pretty predictable. We had 2 functions that did a lot and a main function that did very little other than calling those heavy functions. And we got pretty much exactly the output that you'd expect. However, I'm sure you could see yourself working on a more complicated program. It's slow and you have no idea why. And you can find it very helpful to have a ranking of which functions are taking up the most time. Oftentimes, one really heavy function will dominate the execution time. Like, it'll have 75% of the runtime or more, and then you'll have a good idea of what to optimize. Next, we'll check out Valgrind. So first you compile your code. No special flags here. With gprof, we sort of put the profiler in our executable. With Valgrind, we're going to run the profile on the executable by calling Valgrind. And then it generates a report, callgrind.out. a bunch of numbers. Seems to be a timestamp, but I can't tell exactly what it is. And then, yeah, you can open it similarly to what you did for gprof. So I'll go through these steps on Aviary, but interestingly, it won't work, and I was kind of surprised to see why. I'll show you. Just to be safe, I'm going to compile it again without PG. Valgrind probably doesn't depend on what flags you put in, but I'd like to follow the instructions on the slide pretty closely. And then this will likely take, okay, I didn't have to solve for that much time. I was going to say it will likely take a bit longer than gprof, and it did, but thankfully not too long. So what's that next step again? Cache grind, call grind.out, whatever. This one's the new one, and these two are what I was testing with before. I just remember the numbers. Then what's going to happen when I press enter? We're going to see some very useful, cool information. Nah. Could not connect to display. That's kind of dumb. Aviary doesn't have a display. This is a terminal. It's a headless system. We talked about this in the first class. So are we stuck? Do we need a GUI for this? As far as I know, yeah. But check this out. Ah, sweet. I'm already in the place where I downloaded this. I'm just going to download it again for demonstration purposes. Plus, you can never have too many SCP examples. Sweet, and I already had the command in autocomplete. So now it bears reminding that this terminal tab is on my computer, and this other one is on Aviary. So this is happening like on the Mac, on the laptop you see right here. So you might think to do the exact same thing, the exact same command that we did on the Linux-based Aviary system, but you'll get a big fat command not found if you do that. Luckily, the slides sort of already had some troubleshooting info. For whatever reason, the Mac version is Cache grind. Cool. So this came as a bit of a surprise because I don't have this app. I've never seen it before. This must be the terminal creating a GUI and then basically building it for display. This one's quite a bit more informative than the gprof output. If I had to profile some C code for some reason, I would probably use this, but it gives similar results. In fact, Heavy Computation 2 and Heavy Computation each take up exactly 50% of the runtime, or at least they did in that example, or in that execution. And of course, note that functions call other functions. So main is listed as taking up 100% of the execution time. But of course, we're looking at the functions that main calls. And you can go as granularly as you like. This program only has a main line that calls a couple of functions. More complex programs would have more complex call structures. Just looking around to see if there's anything else worth pointing out. We could see some familiar names in this list, like memcopy, memset. sysmalloc free. So everything that our program did is listed here, but the running time of everything except those two heavy computations was so short so as to be irrelevant. Things like free are shown to take up 0% of the runtime, even though they probably actually took up something like 0.000000000, and so on, 1%. It's neat. But again, you'll probably never use these tools ever. You should just know that profilers exist and be willing and ready to learn what profilers exist for your language of choice and how to run them. And I suppose this example also showed how to interpret the output, kinda. But it was mainly me saying, hey, profilers exist. So that's actually it for this set of lecture slides. I've been looking ahead, and the next few lectures, or should I say last few lectures, because we're almost done the course, are actually really short. So I'm pretty likely to just blaze through those, and then we can decide later what we want to do with the excess class time. I'm thinking just a bunch more office hours. Come in if you want to ask questions about the assignment. Otherwise, chill out at home and then get stressed out about the assignment from the comfort of your own home. So, learning outcomes, we've kind of done this. This is just the start though. The idea is that once you have identified what parts of your code are taking up most of the execution time, you can use the techniques discussed in upcoming lectures, such as later today, such as in 2 minutes, to actually speed them up. So let's go to August 6th. This is Monday's lecture. Crazy. Hope you all had a good weekend. I'm going to skip this one because we already talked about assignment 3 earlier on. Regardless of how quickly I go through the next few lectures, and that's probably not a worry that I need to bring up because I won't complete the course on Thursday. But what I was saying is that on Monday, I'll release the test suites for question 3, and we'll go over those in class so you have a bit of a better idea of what to expect.
For assignment 3, do we need to use profilers?
Profilers?
Yeah.
Nah. Performance isn't really a focus here, and it could be really interesting to say, like, your zalloc function has to meet these performance goals, but nah, I'm not doing that. So this lecture goes back to optimization. What do you do once you've gotten some good information from your profiler? And we're also going to revisit modular design, talk more about coupling and cohesion. So there are two main metrics of measuring program performance, or what it does. Time complexity, you're likely much more familiar with. It's how long a program takes to do its thing. And space complexity is how much memory it needs to do its thing. And we often use way more space than we need. Why is every app now a Chromium instance that uses several gigabytes of RAM? Two examples of bad space optimization is sparse data sets. So there's lots of unused space. And when you have a high volume of data. So as an example, consider naively implementing some sort of video storage scheme. You have a 4K video, it's 60 FPS, and you want to share it. Each pixel in each frame is 3 bytes, one each for red, green, and blue. So how much data per second is this? So 3 bytes per pixel. How many pixels on the screen? Well, we have 3,820 to a row and 2,160 rows. Hey, 2160 reference. And then you would have 24 million bytes or 24 megabytes for one frame. But we're running at 60 FPS, none of that cinematic 24 or whatever. 1.4 billion bytes, 1.4 gigabytes. That's 1 second of completely uncompressed video. Could go a bit further even. 60 seconds in a minute. 60 minutes in an hour. Then maybe you're storing a movie that's 2 hours. How many commas even is that? Million, billion, trillion. I've pirated plenty of movies in my day, but I'm pretty sure they weren't 10 terabytes large. Whoever's making these file formats must be doing something far more clever than just storing every pixel directly. And this is actually a good example of why optimization still matters today. Computers are plenty powerful, and you don't need to squeeze every last bit of performance out anymore. But storing video is a totally normal thing to do, and if you just didn't pay any attention to optimization while doing so, you would start demanding that customers buy 10 terabyte hard drives for the sake of storing a single movie. Don't do that. Very stuttery. Yeah, I was just thinking of like downloading video. Imagine streaming that. You'd have to hope that no one else in the house is playing any online games. So compression is one way to save space. You analyze the data to find redundant data, and then basically take away that redundance. Two types of compression are lossless and lossy. Lossless compression reduces the size of an input without losing any information from the input. If you compress it and then decompress it, you can end up with the exact same thing that you got originally. So let's say the compress function or a lossless compression algorithm. If you decompressed it, you can assert that the original and the decompressed version are the exact same. .zip files are a great example of lossless compression. So is the FLAC file format. And I haven't worked much with FLAC files, but for zip, it usually isn't that much better than the original copy in terms of storage. Like a file that's a couple gigabytes large might get a couple hundred megabytes smaller, but it's not really that good. Still useful for sure, but you can get much better space savings if you make compromises in other areas, such as, well, information. Lossy compression reduces the size of the input by discarding information. Usually stuff that's considered unimportant. Compressed audio would take away frequencies that humans can't hear. Lossy compressed video and images would take gradients that where humans can't tell the difference between the colors involved and sort of crunch them into single colors. And so lossy compression algorithms produce an approximation of the input after decompression. So if we run the same code as last time, take some data, compress it, and then decompress it, this assertion would fail because the original and the thing that we compressed and decompressed are now different. This makes the computer very angry, might make people who care a lot about quality in their file formats, like people who are really enthusiastic about music or video, pretty mad. But for all practical purposes, it's a very good idea to have lossy compression. Yeah, I guess if you're following along with this from the lecture recording, lossy compression says you're welcome, because otherwise this video would be a couple terabytes large. Some pretty familiar lossy compression schemes, JPEG, MP3, H.264. JPEG and MP3 I'm sure you've used before, maybe not H.264. And the article that this links to is very neat. Strictly optional. This won't be on the final exam, although pretty much everything else in these lectures can be. And I know you're all stressed about the final and your assignment and other courses and life and stuff. But if you have a moment, check this out. Narrates an example where it does some lossy compression to get the image down to 7% the size of the original. Or maybe even more. I don't remember the exact numbers. But it goes into detail about some pretty cool techniques that it uses. So compression gives a really good space advantage. The space complexity of your program goes way down, but there has to be some sort of trade-off, right? You can't just get this for free. For one, it can involve some really tough math. Take grad studies if you want to learn more about this, I guess. I sure haven't. I've been focusing more on theory of computation and stuff, but I'm sure that information theory is an interesting path to go through as well. The actual compression algorithms are out of scope for this course. Of course, if you're curious, go read that article. But we can look at things from a lower level. And spoiler alert, these are going to turn out to be a lot more pain than they're worth, but it's still good to know what options are available, because you might end up in a situation where it's your only option. We want to change how we represent the data and use a data structure that only uses the space that it needs. We saw this with strings. At the very beginning of our string example, we just had an array with a constant size. I don't remember how many characters it was, but it was a lot. And if you're just storing something like hi, that wastes some space. It was much better for us to dynamically allocate the char array for our string, because then we're only using the space that we need. But we could go even further. And also, this might still end up wasting space if you have a string that's initially long and then end up resizing it or storing a smaller string in its place. So our linked list version of the string class came in handy in order to only store space for the characters that it needs. So maybe instead of an array with a constant size, you could use a linked list or a binary search tree. And for matrices, the most obvious implementation would be to store every element of the matrix. But in lots of practical applications, matrices have a lot of 0 elements, and it's much smarter to only store a list of the non-zero elements and where they're located. More, of course, in Comp 2140, which should be winding down right now, and Comp 3170, the sequel to analysis of algorithms and data structures, where you'll learn more about this sort of stuff. So take a look at this piece of code. This is slow. It's doing a lot more than it should. And I'm just going to, I don't like to ask classes questions because I've been in way too many situations where the prof goes like, okay, please answer this question, and then it's just awkward silence. But I'm still going to keep this up for a little while longer so you can at least think about it before I give the answer. Plus, on your side, answering questions in front of a whole class is nerve-wracking. I don't want to put you through that. Why is it slow? Well, first I'm going to press the down key on my keyboard just in case the slides have an example that's better than anything, or any way I could explain it. I don't quite remember. Nope. Okay, it's up to me to ramble. This is the culprit. Dictionary. You might hope from the name that it's a dictionary, as in hash table, but it's not. It's just an array list. So hopefully this is giving you Comp 2140 flashbacks, but for every iteration of this loop, by checking dictionary.contains the word S, it's doing a linear search, going through every element of the array to find the string words, or the string S. And the name implies that it's the entire dictionary, and dictionaries are thick. So this is probably a really long array, and linear searching through it would be bad news. So how would we fix it? Well, I guess we just spelunked through it a little bit. We could maybe pepper it with print statements and nah, print statements probably wouldn't really do anything because this function is so homogeneous. It would just be a whole lot of print statements that have the same amount of time between them. We can use a profiler, and it would tell us that dictionary.contains is taking up most of the runtime because it's doing a slow linear search through a dictionary repeatedly. But how do you actually fix it? In our case, the best strategy is to be smarter about the data structures we're using. A much better data structure for this problem would be a hash table, because hash tables have constant time lookup. We would turn this line into something that takes as many operations as there are words in the English language into something that takes one operation, or at least like one hashing algorithm that most certainly takes less time than a linear search. Actually, I'm curious, and I clearly have time to spare. I want to know how many words there are in English. So somewhere between 780,000 and 1.4 million. Something tells me a hash table lookup would take less than several hundreds of thousands of operations. This is yet another programming practices lesson that we're going to use C as an example for, but is generalizable to pretty much everything. If you have slow code, you should think about the data structures you're using. And changing the data structures should always be your first approach. Oh, and also, I disclaimed earlier about how we're going to look at some pretty low-level ways to optimize for space, and those things will be more trouble than it's worth. That is not, or this is not that more trouble than it's worth stuff. This is genuinely good advice. If your code's slow, think of the data structures. But now we're going to get dangerous. You could want to squeeze out the last few bits. And that is a very dark path you can go down if you really want to. Maybe you're working on embedded systems and you really need to. But that will have to wait until the next lecture. We're really blazing through these, and we're actually at the point where I haven't prepared the next lecture yet, so I'm just going to let you all go in a couple minutes. So we talked about optimization a lot today, both how you would find problems, profilers, and how you would solve them using better data structures. And eventually we'll get back to modular design. So, guess I'll do office hours till 1:45. Stop by my office if you have any questions about the assignment. But for now, have a great day. See y'all.